This slide shows that if we want to do a CFD calculation of a turbulent flow, a number of different approaches are possible. On the left, we have what is called direct numerical simulation, or DNS. We know that turbulent flows are governed by the Navier-Stokes equations, so in theory it's possible to do a three-dimensional, unsteady flow calculation with a grid that's fine enough to capture the motion of all of the eddies in the turbulent flow, from the largest eddies all the way down to the Kolmogorov scales. This would capture all of the detail of the flow field and no modeling would be required. Unfortunately, the number of grid points that this requires makes this impractical for industrial flows, and DNS is only used for fundamental turbulence research. The middle image depicts large eddy simulation, or LES. In LES, spatially averaged Navier-Stokes equations are solved. These are also called filtered equations. On an earlier slide, it mentioned that most of the energy in a turbulent flow is present in the largest eddies. So the idea is that with large eddy simulation, we attempt to directly resolve the unsteady motion of the largest eddies, which is more difficult to model, and then only to model the effects of the very smallest eddies, which hopefully is more amenable to modeling. With large eddy simulation, because you're capturing the motion of the largest eddies, you're still getting a lot of detail in the calculation, and it's still a three-dimensional unsteady calculation. It's not as much detail as direct numerical simulation, but still a great level of detail. So large eddy simulation is not as expensive as DNS, but for many cases, again, the computational resources and the effort that's required to do a large eddy simulation is not practical for most industrial applications. There are lots of LES models available in Fluent, but we don't cover those in the introductory training. And then on the right-hand image, we show the results of a calculation that was obtained using a Reynolds average Navier-Stokes simulation, or RANS simulation. With RANS models, what we do is we time average the Navier-Stokes equations, and these are derived from the velocity composition that we saw on the previous slide. And in this decomposition, all of the turbulent length scales are modeled, and that means that the flow solution contains only values for the mean flow variables, which is what we see in the image up here. This is the most widely used approach for modeling industrial flows, and Fluent also has a lot of different models available for RANS modeling, and this is what we'll talk about next.